So as we move forward in organic chemistry, really what we're going to see is the chemistry of different functional groups. Thus far, we've been talking about substitution and elimination reactions, but the focus of that is the chemistry of halogens. So when we looked at those two reactions, every reactant had a halogen inside of it, and that was part of our understanding of the chemistry of halogens. They can do substitutions and they can do elimination reactions. So what we're going to be talking about now up until the end of the material for the third midterm is alcohols and some of their chemistry. So you got to remember for the third midterm, really that's the only two things that we've talked about is halogens and alcohols. And so when it comes time to decide what kind of reaction is occurring, that's going to be key, is to look and see, am I starting with a halogen or am I starting with an alcohol? Because they lead into two different categories. So with alcohols, the first thing we want to discuss is that the OH group, which is called a hydroxyl group, actually is not a good leaving group. So when we had talked about halogens as being good leaving groups, they were electronegative, and also some of them were larger, like bromine and iodine, and so they could stabilize the negative charge that leaving groups gain after they act as a leaving group. But the OH does not do that. So if we were to pop OH off and if it was to gain a negative charge, relatively speaking, that negative charge is not that stable. So the OH by itself cannot act as a leaving group. By that I mean like a nucleophile can't come on and push it off, and the OH won't spontaneously pop off to form a carbocation. It doesn't want to do that because it cannot form a stable negative charge. However, there is a way that we can make the hydroxide or the hydroxyl group a good leaving group. We do that by protonating it. So protonation leads into some of the concepts we talked about in the first exam material, where we have acids and bases. So if you remember, I talked about drawing the conjugate acid for something. And the idea there was that anything with lone pair electrons can be protonated if you have a strong enough acid. And that's exactly what we're going to do in this case. So I didn't draw them on there, but remember, oxygens in their neutral state have two bonds and two sets of lone pair electrons. So if we use a strong acid, we can actually protonate that oxygen. And in doing that, that is going to make our OH a good leaving group. So here, when we do this reaction, really what we're going to be following is a SN1 reaction with a little bit of a twist. So when we look at the actual reaction that we are doing, it's still a substitution reaction, but now we're using the OH as a leaving group. So the OH pops off, and when we see the mechanism, we're going to learn that here the chloride is the nucleophile. So we haven't talked about halogens as being a nucleophile. We're going to talk about that in just a second. But overall, the same basic idea is occurring with a substitution reaction. We're kicking off the leaving group and we're replacing it with a nucleophile. So in this case, we're turning our alcohol into a halogen. So as you go through making flashcards for the upcoming midterm, that's one of the things you want to remember is most of the reactions in organic chemistry is about turning one functional group into another. I'm starting one functional group and then I turn it into another functional group. So here I'm starting with an alcohol and I'm turning it into a halogen. So we can kind of see why protonating an OH makes it into a good leaving group, because if I protonate the OH, what it is going to turn into is water, and water is fairly stable. So we'll see this more in just a second when we look at the mechanism. But overall, this is a substitution reaction, and with this reaction in particular, it is an SN1 mechanism. So with this, we don't really get the SN1 EN1 or E1 tie-in that we had with halogens. So we'll talk about that more in just a second. So when we look at the mechanism, this is the idea of acid catalysis, and we're going to use this quite a bit as we go along in organic chemistry. The idea being, if I add a little bit of acid to a reaction, it can speed up certain reactions quite a bit. So it'll act as a catalyst. When we do use an acid in a reaction, inevitably the first step is going to be a protonation. So just remember that acid-base reactions are some of the fastest reactions that we know in chemistry. So if I have an acid present inside of a reaction, the first thing that's going to happen is protonation. So when we look at this, we have our starting alcohol, we have our strong acid. And inside of our alcohol, the only place where we can protonate is the oxygen, because the only thing that has lone pair electrons is our oxygen. So this is a simple acid-base reaction. So we kind of talked about that in the beginning. This is why we talked about it in the beginning, because we're going to see acid-base reactions like this continually as we go through organic chemistry. So literally all we're doing is protonating the oxygen. So here the lone pair electrons on my oxygen are attacking the hydrogen. So lone pair electrons attacking an atom forms a bond. So one of these OH bonds are formed from this arrow. The next thing that happens is we break the HCl bond. So the electrons in this bond move to the chloride in this case. And a bond attacking an atom forms lone pair electrons. So if we look at this, the chloride has 3 sets of lone pair electrons. Here it has 4 sets of lone pair electrons. Also, when you look at the charge, electrons are leaving the oxygen. Initially, the oxygen is neutral. Now it is going to be positively charged. Here, electrons are moving to the chlorine. The chlorine here is neutral. Electrons are moving to it, so it's going to have a negative charge. So remember that this is still fundamentally a SN1 type mechanism. And this is one of the most important ideas in organic chemistry, is to not look at things being distinctly different. If you can glom them together or try to see similarities, the amount of material that you need to learn is drastically reduced. So here, step 2 and step 3 of this mechanism is just the same mechanism as the SN1 mechanism that we talked about in the previous chapters. The only difference is that we've added a protonation step. So with this, I know the next step for a substitution, SN1 substitution reaction, is I got to kick off the leaving group. I got to kick off the leaving group and form my carbocation. So here now you can see where my OH has become a good leaving group. Now it is almost to water. And when we do this during the removal of our leaving group, in this case water, we break the carbon-oxygen bond and those electrons move to the oxygen. So a bond attacking an atom forms a set of lone pair electrons. So here, when we kick out this protonated OH, so we protonated the OH, when it acts as a leaving group, now it forms water, which is very, very stable. So protonating our OH makes it into a good leaving group. This reaction would not work without that acid catalyst. So here we pop off the leaving group. Electrons are leaving the carbon, so we end up forming the carbocation, which is distinctive for SN1 reactions and then also E1 reactions. So we're going to look at that here in just a second. But now that we have the carbocation, we can continue on. In the next step of our substitution reaction, after we form our carbocation, what happens is nucleophilic attack. And what's our nucleophile is the chloride anion here that we made after HCl lost its hydrogen. So we haven't talked about chlorine or halogens themselves being nucleophiles, but if you look, they have everything that is needed to be a good nucleophile. They have lone pair electrons and they have a negative charge. So halide anions actually act as a good nucleophile. So we're going to see this as we go along, where there's lots of different nucleophiles in organic chemistry, and periodically we're going to introduce you to new ones. So here we have introduced the our halogens as being a possible nucleophile. So in the third step of our substitution reaction, we have formed our carbocation. My chlorine can now act as a nucleophile. Lone pair electrons attack the carbocation. So lone pair electrons attacking an atom forms a bond. So we end up forming this carbon-chlorine bond during this reaction. Electrons are moving to the carbon, so it goes from positive to neutral. And then here, electrons are leaving the chlorine, so it goes from negatively charged to neutral. And then just remember overall in the end reaction, we do the substitution, we kick out the OH, we replace it with the nucleophile, and then we also produce water during this reaction.